Hey students, I thought I'd make a quick video here on when to use which equation during the thin film. In other words, we have one equation which says 2t equals to m times the number of wavelengths in the film. And we have another equation that says m plus a half times the number of wavelengths in the film. But what makes it kind of confusing in picking on which one to use is sometimes, let me just take this one for example. This would be the appropriate equation for number 23a, where it says, find the color of the light in the visible spectrus right here, strongly reflected. But yet, this would also be the appropriate equation in number 27, where they said the material have an index of refraction used as a anti-reflective coat. And so why would this same equation that is used in 23, which gives us a lot of light reflected, be the same equation in number 27 when we're trying to get a minimum light reflected? I mean, is this equation supposed to be for a lot or a little reflected? Which is it? And sadly, it can be both. And that's what makes it kind of challenging to decide which one to use. So let's come back to these two, and I'll then point out why this one equation is good for both of those. Let's do a more generalized discussion and see if we can set up a little thought process that you might want to run through when you're looking at a problem to decide which of these two equations is appropriate. All right, so let's start here. And let's say that we have a thin film and it has a thickness T. And if you first go to analyze this, you'll do something along these lines. You would say, so some light comes down, hits the top layer and bounces off. Let me call that ray number one. Part of that ray then transmits through and bounces off. So let's call that ray number two. And if I'm looking at the interference of ray number one and ray number two on reflection, and I say that because there's also going to be this piece that goes through transmitted and this piece that goes through transmitted. So we could say beam 1 and 2 is also transmitted. In fact, we could go on and have a bunch of beams like 3 and 3 and 4. Fortunately, though, we don't, because if we can just figure out what's going on with 1 and 2, the same thing happens with 3, 4, 5, 6, 7, 8, 9, 10, and infinite. So we can actually analyze this by just looking at the interference of 1 and 2 on reflection or 1 and 2 on transmission. So let me ignore the transmission. Let's just keep it simple here at the beginning. If I was looking at whether 1 and 2 interfered constructively or destructively, I guess I would say this. Number 2 goes down and back. That means the path difference, which I've been using the symbol delta for, is 2t. And so I'll put a little if statement here. If 2t then is an integer number of wavelengths, and so m equaling, let me not write it there. Kind of messed up what I wanted to do. I want to make a little chart here. So if 2t equals an integer number of wavelengths, and then maybe up here I'll say m can be 1 or 2 or 3, okay, you would get constructive interference. That is, a crest of number 1 would line up with a crest of number 2. And then for that matter, also a trough of number 1 would line up with trough of number 2. In other words, they would be in phase. Now, there's a couple of subtleties here. The first subtlety is that it would actually be the wavelength in the index. And if you go back a chapter, we learned that the wavelength in free space then has to be divided by n the index of the thin film. So this n would be the index of the thin film, not above it or not below it, whatever material that is. It's of the thin film. Now, that's not to say we don't need to look at these other indexes. That's coming up. But in this equation, the n is the n for the thin film. Okay, now, again, if. Because, we can make it any thickness and any wavelength, so they may not match. So I'm just saying if. If those match, I'm going to write here, then you will get bright. If you want to write that as maximum, constructive interference, whatever word you want to put there, that's what you would expect to get. Okay. All right. Now, notice I didn't say anything yet about the whole shifting of a phase during reflection. And so I'm going to then put kind of a little table here and say, well, this would be true if I had 0 phase shifts. Okay. Now, I'm kind of hoping that made sense, because that's kind of my starting ground with my thinking, is that this, if this is true, I would get constructive interference because, I'm talking about no phase shifts, and I'm also, talking about just simple integer multiple of wavelengths. Okay, great. Now, I guess that would also then, as an extension of this, say that the m plus a half of, again, wavelengths within the medium would be where I would get dark or destructive or minimums. All right. So if the problem, is talking about reflected light and there's no phase changes, I could then decide whether I'm going to use this equation or this equation depending on what they're looking for. Are they looking for a lot of light being reflected, so bright, or just a little bit, so dark, so constructive and destructive? Okay. Now, let's keep talking, because I would say then that what I just described is true for the reflection of the light. Because what if the problem wasn't asking for the reflected light, but the light that went through and came out the other side? And so, like, maybe this is a thin layer of oil on water and there's a fish down here, or a camera underwater, and you say, well, what would the camera see? Or the diver, and up here is the sunlight, or something like that. Or more realistic, I'll take off my glasses. I don't know if they would even show in here. They're not supposed to show, but I have a thin film put on my glasses so that it would help reduce the amount of light reflected. And so, reduce it on reflection, I would be looking at this equation. This would give me the mathematics to find how much little light upon reflection. Now, of course, that's with no phase shift, so I need to be careful because it's going to get more complicated here in a second. Okay, but what I guess I want to do is kind of put a little dotted line here and say, well, what about the light, that gets transmitted through the thin film? Well, because of conservation of energy, and you could even then count it, 1 and 2 then would be the opposite. I just like to do the conservation of energy. And so if this same equation, 2t equals an integer number of wavelengths, and the whole reason we are getting, bright upon reflection is also then why you would say it's a dark or a minimum on the transmitted light. So again, deciding on which equation to use, you got to be asking yourselves, not only are you looking for bright and dark, but you're also looking for this question, are we looking at reflected light or transmitted light? Because again, because of conservation of energy, if the light's being reflected, it's not being transmitted. And so I'm here. If this one is saying the light is dark, not being reflected, well, that's because it is being transmitted. So deciding on which equation to use, you are want, oh, let me finish writing here, bright or maximum. You need, again, decide those two important factors. And of course, there's a third with phase change, which I'll explain in a moment. But you want to ask yourself, am I looking for light that is reflected or transmitted? And am I trying to get light that is either bright or dark? And so these were our 4 options so far. There's going to be 8 options by the time I'm done here. But decide between these two, then decide between bright and dark. And then notice there's only 2 equations. So right now there's 4 scenarios, but only 2 equations. That's why the same equation could show up in one scenario and then yet another scenario. And again, that's what we're going to see here in comparing 23a with 27. They're both going to use, I believe it's the m plus a half equation. Yet there is difference in them, okay? And the reason we are going to end up using the same equation. Okay, now we do have one more thing to think about. And let's go back to this starting point of 1 and 2. So far, all of my thinking has been without any phase shifts. Maybe I'll use my fingers to kind of indicate if I had one being a wave and it's up, and another one being a wave and it's up. If one undergoes a phase shift, I'll have one up and one down. Well, they'll tend to cancel each other. Or maybe this one goes under a phase shift. Doesn't matter which one undergoes a phase shift, but if you have one of them undergoing a phase shift, that completely reverses things. See, in this equation here with no phase shifts, they were adding up in the same direction, and now they cancel. And so what happens, instead of being bright, it becomes dark. And so this equation now becomes an equation that I would use with one phase shift upon reflection looking for dark. And this here then would be just the opposite. See, they were getting destructive because they were opposite. And then if one undergoes a phase shift, they're back in alignment. Or if the other one goes under a phase shift, they're back in alignment. So this one that, I was thinking it was dark with no phase shift now actually has constructive interference. And so now it's bright. Okay. And again, using the principle of conservation of energy, if this equation right here on reflection is dark, the reason it's dark is because the energy got through, and so this would become bright. Or you just might say it's the opposite of that one. Okay, and again, this one then, because this one, is giving the equation right here bright on transmitted, then it would be dark because of, again, conservation of energy. All right, so these are the 8 scenarios and 3 questions you have to ask yourself, right? You could have, something with no phase shift, so it would be this column. You could have either the light being reflected, so it would be using these 2, or transmitted, these 2. And then you would be looking at either light or dark. Or you could have one phase shift. Okay, so if one of them, either beam 1 or beam 2, undergoes a phase shift, then I can kind of look at this column and do that kind of logic. Okay. Now, you might ask, well, what if both of them undergo a phase shift? Well, both of them is really the equivalent of none of them because it has to do with the difference in them. And so if I just use my fingers again and say, okay, well, one of them comes up with a phase this way and the other one comes up with a phase this way, and they both undergo a phase shift, they're both still in the same direction, so you're still getting constructive interference. So this column, if either none of them or both of them have a phase shift, and this column, if one of them have a phase shift. It doesn't matter which one, but just one of them, okay? So, again, ask these 3 questions. These are the 3 questions you want to ask. Number 1, are we focusing on reflected light or transmitted light, okay? Number 2, does it have either 0 or 2 phase shifts or 1 phase shift. And then number 3, are we looking for bright and dark? And that would decide which equation we use. Now, one more thing I should probably say, when do they have a phase shift? Well, they have a phase shift when the light coming in is at a lower index and hits something that's higher. Then there would be a phase shift. And that might be best illustrated as we kind of wrap up this video and say, okay, so now let's answer this question on which one to use. I won't put in the numbers. I'll save that for a different video and actually do the solution. But for these two questions, I would start off this way. And let me just get my chart handy, okay? So maybe I'll fold it right here. Suppose it couldn't even hurt to have this chart handy during the exam. Just kind of put the chart here up at the top of the screen. Okay, maybe here. And then I'll look at number 23A, and we'll even do B, but why don't we do 23A first here? And so when it says an oil film has an index of 1.45, floating on water, is illuminated with white light at normal incidence, the film is 280 nanometers thick, find A, okay, and this is going to be my 3 questions. The color of the light in the visible spectrum most strongly reflected. Okay, so first question. Are we looking at reflected light or transmitted light? Okay, let me just write here, 23A. So clearly, strongly reflected, we're in this category. Okay, so I'll ignore the bottom part of this table. Okay, now the next one is, how many phase changes do I have? Well, here's where maybe I need to draw it here. Well, this will be my thin film. But the oil is floating on water. So down here would be my water. The thin layer is going to be my oil. And then I'll have air above it. So some numbers to work with. The index for air is 1. Oil can vary a lot. And in this case, they are telling us it's 1.45. And water, you might want to look that up in the table, but it's 1.33, okay? So when a beam comes down and bounces off, right there, and going back to calling that beam number 1, it's going from 1 to something higher, and so yes, that one undergoes a phase change. So I'm going to put a little circle around it. But the one that then hits right here is going from a higher index to a lower, no phase change. So bringing my chart into play, I would say I'm looking at this column, 1 phase change right here. Okay, so I got reflected light with 1 phase change. So it's going to be one of these 2 equations. And then coming back, it does say strongly reflected. So I want constructive or bright. So that it's right there. This one right here is bright with 1 phase change on reflection. And so the equation I want to use is 2t equals to m plus a half wavelength and free space divided by the index. And so that's the equation I would use for 23A. Now I'll come back to 23B, but I wanted to compare this because this is what I really wanted you to see is, let's look at number 27. 27 says, a material having an index of 1.3 is used as an anti-reflective coat on a piece of glass, index 1.5. Okay, so if I draw this scenario, my thin film, my anti-reflective coating, that's kind of what I was talking about earlier with my eyeglasses here, has an index of 1.30, and it's placed on glass, and of course, it's coming from air. So the light comes down, and then notice the reflection is going from air to something with a higher index. So I'll put a little circle, and that's kind of like we had back here in number 23. So there's going to be a phase shift there. And then this beam continues down, and so this will be beam number 2. But this one is going from a lower to a higher, and that's a little different than we had in number 23A. We had it bouncing off something of lower index, but here we have it bouncing off of something higher index, the glass. And so I'm going to put a circle there. So they both undergo, okay? And so coming back to our little chart with our 3 questions, the first one being how many phase changes I have in this problem 2 phase changes. So it's going to be in this column, okay? And it was kind of implied here, a material having an index of refraction is used to anti-reflective coating. So in other words, we're looking at reflected light. So in this table, I'd be looking right here, you know, in this, well, so in this area for reflection, and in this column for 2 phase changes. And because it says anti, we want it to be dark. So there it is. So this is the equation that would be valid for dark or destructive interference on reflection when there are 2 phase changes. So this equation would be 2t equals to m plus a half lambda naught over n. And so surprisingly, it's the same equation. Yet, in 23A, we had strongly reflected, and in 27, we have weakly or destructive. Yet, same equation. And that's because we have a different scenario on the reflection. And that can be confusing. Now, just to finish up for completeness here, let's also look at 23B. 23B says, and so let's remind ourselves, we're back here with this scenario with the oil. Okay, we got air, oil, water. 1 phase change because the index of this oil is pretty high. Because there are lots of oils that are under 1.33, so then we would have a 2 phase shift scenario. But this oil is a thicker, higher index oil. It's kind of probably a motor oil. And so this is our index, or this is our scenario 1. So coming back to here, I'm going to be in this column, okay? It says, the color of the light of the spectrum most strongly transmitted. Okay, so I would jump down to here because I'm looking at transmitted. 1 phase change here. And strongly means bright, and so I would be looking at this equation for 23B. Oops, I lost my place. What did I do? Transmitted, 1 phase change, strongly, right there. 2t equals to m lambda naught over n. Okay? And of course, probably makes sense because we already did this, and so you can kind of shift to that one. But anyways, hoped all that helped. Wasn't so much interested in trying to help you with 23 and 27, at least in this video, but to set you up with your thinking, given that there's 8 different possibilities because of, you know, a choice between reflection and transmitted, 0/2 phases with 1 phase, and bright or dark. So it's 2, 4, and 8. 2 times 2 times 2. 8 different possibilities, but only 2 equations, and that's why different scenarios can use the same equation, and that's why it can be really hard to decide which equation to use. All right, hope that helps. Take care.